Remember when you were a kid and you were super excited to go to the amusement park? They had that awesome new roller coaster, the one with loops that went upside down and everything, and you just couldn't wait to get on and blast at warp speed through the curves. Then, after waiting almost an hour in line, you got up to the front and found out that you were 1 inch too short for the "you must be this tall" sign. You tried standing on your tippy toes and everything. The ride police, though, ultimately busted you. Denied. All that awesomeness and no way for you to take advantage of it. Using FPGAs for DSP work has been kind of like that. You know that an FPGA can run circles around your conventional DSP processor, both in performance and power consumption, but they never quite had everything you needed to take advantage of it. No analog input, no low-cost FPGA that could handle your problem, no just right FPGA DSP development kit. It was that roller coaster all over again. Hi, I'm Amelia Dalton, host of Chalk Talk. Today my guest is Tom Hill of Xilinx, and we're going to talk about the new Kintex-7 DSP development kits from Xilinx that will finally get you onto the roller coaster of FPGA-powered DSP. It's kind of awesome. Finally. Before we get started, I want to remind everyone that you can click on that Download Now button below your player. There you can download a free product brief that further expands on this topic. Thank you so much for joining me today, Tom.
It's great to be here.
So in previous Chalk Talks, we've chatted about different Xilinx FPGAs, but this is the first time we're going to talk about a 28 nanometer family. So how does Kintex-7 FPGAs compare to Xilinx's previous generation of devices?
That's a great question, and specifically what I wanted to talk about was how they compare to previous devices for DSP applications, since that's my realm at Xilinx. And the Kintex-7 device, we like to think of it as Vertex-class performance at half the cost and half the power.
Okay.
This device is built on a new 28 nanometer HPL process, and it does offer what we bill as, twice the cost performance. And the process does deliver dramatically low static power as well as power savings in some other areas. It's consistently shown to be about a 50% power reduction. So for folks that are doing, DSP development, Kintex-7 is really sort of the premier device in our 7 series device family for DSP. And it's not just limited to DSP. This really is a system-on-chip platform, so the device does have a lot of hard IP that comes along with it.
Great.
Including the DSP blocks, of course, but it's got onboard memory, it's got dedicated blocks like PCI, Tri-Mode Ethernet, and high-speed serial transceivers for high-speed connectivity. So it really is a complete system-on-chip platform for DSP.
So a lot of people use traditional DSP processors. How does this compare to using one of those?
Yeah, another great question. And yes, there are a lot of people that currently are using DSPs, and a lot of applications are well served by DSPs. The big trend that you've seen in DSP processors is they are getting faster, but the actual clock performances tend to be incremental, like they go from a gigahertz to 1.2 gigahertz. Whereas Xilinx has been able to basically double the DSP capabilities of chips from generation to generation. But with the processors, they've been adding multiple cores, and even within the cores, they've been adding multiple arithmetic units within the cores. So there has been some parallelism that's been introduced, and this has helped drive the performance up, but this is still just a little bit under a tenth of what we can do on a Kintex-7 device.
Wow.
So again, I'd say our largest advantage is just the raw DSP performance we can deliver. But then the other area that FPGAs are universally used for is to interface to high-speed analog. If you've got an analog interface that's, between 1 and, 30 or 40 megasamples per second, you can consume that sample rate by a processor. But when you get above that, and we've got partners today that provide analog input up to 3 gigasamples per second.
Wow.
You need an FPGA to interface. So for any application, it requires high-speed analog. And this is, all your wireless, software-defined radio, a lot of military applications. I mean, they're all, clearly in this category. They universally use FPGAs to interface to the high-speed analog interfaces. So that's another, key benefit of the FPGAs as well.
So, Tom, what makes Kintex-7 such a good device for performing DSP arithmetic operations?
Well, the heart of the Kintex-7, as well as our whole 7 series and Zinc devices, is a DSP processing element called the DSP-48E1 slice.
Okay.
This does perform over 30 different arithmetic operations. One of the things that's unique about it is it's dynamically configurable on a clock-by-clock basis. So if you wanted to perform, say, a large multiply or a complex multiply over a series of clock cycles, you can actually write a little state machine to change the behavior and dramatically save resources. But then it is a very flexible architecture. There are 2 of these that are connected together in a tile through 5 high-speed interconnects, and it can perform arithmetic operations from the 25 by 18 that comes in one. It can scale all the way up to, say 42 by 18 without using the pre-adder, or 36 by 18 using the pre-adder. So it does scale to a lot of different precisions depending on what you need. In fact, you can do a single precision floating point operation in one DSP-48 tile or 2 slices.
Okay.
So this can be configured to do a lot of different arithmetic operations. It's got some really unique features, like it's got a pattern detector block, which is used in the different rounding modes, which are common in wireless and military applications. And it also has independent access to the pre-adders, the multipliers, and the accumulators. So it's just a real flexible block. Fortunately, it's well supported by our IP cores as well as our tool flows, which makes it very accommodating to a lot of different types of arithmetic calculations that people perform.
This sounds great. So what's the best way to get started, especially for those of us who may not be familiar with Xilinx?
Well, Xilinx, probably about 3 years ago, we announced a pretty robust initiative to put a lot of effort behind targeted design platforms. And conceptually, we introduce platforms at different levels. We have at the bottom, which are called our base platforms, which are our basic development kits for the silicon. But then we build on top of those, and we're able to provide what we call domain platforms, which is what my DSP kit is. This platform strategy has really served us quite well. For one, it lets customers buy less hardware and be able to use it to do a lot of different things.
Very good.
And it's also allowed us to align our ecosystem around some of the standards on this, like our FMC. We've got a standard connector on the board for daughter cards for I/O, and we now have over 100 different FMC cards that are provided through that standard. So,
wow.
Regardless whether you're doing DSP or video or some market-specific stuff, Xilinx has a lot of different platforms, a lot more than any other programmable vendor on the market, and you can really look them all over and see which one is closest to meeting your needs.
Great. So what do you have specifically for DSP?
For DSP, we just recently announced our Kintex-7 FPGA DSP Kit. This is everything you need to get started with DSP in a box. It does include all the hardware you need. It does come with a 1-year entitlement of our ICE Design Suite software, as well as reference designs, documentations, and cables. This is for sale now, and current price is $39.95.
Wow. Okay. $39.95. I've got my credit card right here. Tell me what's on the board.
I've got my credit card reader right here. Again, going back to our platform strategy, this thing is built right on top of our base evaluation platform.
Okay.
In fact, we were able to release the DSP kit on the exact same day that we released the platform. So this is
great.
This is really kind of highlights how this platform strategy lets us get these kinds of platforms into the market a lot sooner. And the baseboard, it does have a Kintex-7 385T device on it, which has a number of, I think it's got 840 DSP-48E1 slices. And then the board itself has PCI interface. It's got JTAG, Ethernet. It's got the usual interfaces that you would expect to find on a development board like this. The baseboard itself has been wildly popular since we announced it. And of course, anybody that does buy the baseboard could just buy the extra hardware and upgrade it to a DSP kit. So we have upgrade paths as well.
So, Tom, this is a DSP kit. How do we interface it to analog signals?
Well, each DSP kit does come with an analog interface daughter card.
Okay.
This card is developed by a partner for us called 4DSP, and it's the FMC 150. And this is a very high-speed analog interface. It has a dual 16-bit 800 megasample per second DAC interface. These are Texas Instruments DAC chips. It's got a 250 megasample per second 14-bit dual-channel ADC interface, as well as a clock synchronizer, jitter cleaner, The chip does have an onboard oscillator, so you don't have to hook it up to an external clock source to run the demos, but it does support the use of an external clock, which is common in development. And then one of the other, I think, key features of this board is all these data converter chips are programmable, and there is an I2R interface on there to accommodate that. And this is hooked up through the FMC header so that we can gain access and reprogram those devices through the FPGA. So these chips are designed to be configured through the FPGA through an FPGA interface.
Very cool. So what else comes with the kit? Does it include design tools? Are any of them high-level design tools?
It does include design tools. It is worth kind of talking about this a little bit because DSP, it's a bit of a unique design realm for FPGA designers because it's algorithmic and it's mathematical. And because of that, you can certainly develop your applications in RTL, which a lot of people do. But there really is a need to tie these tools into higher level environments like C and the MathWorks are really the two prominent ones that we're focused on. So this kit today does ship with our System Edition software, and this does include Xilinx's System Generator for DSP product, which does enable the use of the MathWorks MATLAB and Simulink modeling environments for FPGA design, and it does include a Xilinx DSP block set with about a little over 100 Xilinx-optimized DSP building blocks for the Simulink environment. And this is a very popular way to develop DSP accelerator blocks within our devices.
So, Tom, what are the key features of the reference designs that we would find useful for DSP applications?
That is not only a good question, it's a very important question.
Oh, great.
And I think people may overlook just how much value is delivered in these reference designs. You're going to get a board, you're going to get your daughter card, you're going to get your tools, and there's some design in there. But this design is really one of the crown jewels of the whole kit. It is just a kind of a typical DSP-type analog interface. But this thing has been performance tuned to really maximize what you can do with these data converters and with the Xilinx fabric. So, for example, we've got a 250 megasample per second ADC coming in here. We're actually bringing the data onto the chip using almost the full capability of the ADC at 245.74 megasamples per second. So to do this, these analog interfaces are actually a fairly complex clocking problem. You've got asynchronous clock domains. You're bringing clocks in from the outside world. You've got to clock your board. You've got to interface it. So we've found that one of the most common reused parts of this design is actually this analog interface. Now this comes onto the board, and then we are doing pretty classic digital filtering operation, which is to perform digital down conversion down to baseband. Then we loop it back around, and then we perform digital up conversion back up to the DAC interface. And we are clocking the fabric at 491.52 megahertz, which is extremely high performance. This is a multiple of the WCDMA LT wireless spec. So this is a key metric, and it really highlights the performance capabilities of the chip itself. In addition to that, analog interfaces are very sensitive to kind of variances, heat, temperature, things like that. And we actually have an automatic calibration interface on there, which will dial in the I/O delays
Nice.
to make sure that we get a clean interface on there, which again is reused as well. So we consider this reference design a product, not just an example. We do update this for each software release. It's fully supported, and it is a key element of the kit. And quite frankly, this reference design alone could either enable somebody who's never done analog interface design before the chance to do it, or it could save somebody weeks, if not months, of development time. So it's a very important part of the kit.
All right, this looks like some great stuff. So how does someone new to Xilinx design flows figure out how to use this kit to develop their own custom DSP applications?
Yes, having a kit is one thing. Being able to use it to do stuff is another thing.
Indeed.
And we understand that. We provide a real quick getting started guide with the kit, first of all, which we really want you within 30 minutes to open up the box and see the design running. And it's really meant to demonstrate your kit arrived, it works, kind of what it does. But that doesn't necessarily prepare you to go off and develop a next generation wireless application.
True.
So we do provide a design tutorial. And there are, even with RTL design, There are a lot of, sort of unique design tricks that a DSP RTL designer would do that somebody may not be aware. So we include some of these into the tutorial.
Nice.
How do you validate correct filtering operations from an RTL simulator? So we include this design tutorial, which takes you through how to verify a DSP RTL design. It then shows you how to interactively modify the analog interface. You can tune the analog interface with gains or sample rate settings like that.
Nice.
And then it shows you how to then make a change and then recompile the design to be able to re-hit that 491.75 megahertz frequency. So it really has, the whole steps. You get to run it, you get to interact with it, you get to modify it, and then you get to completely regenerate it and reprogram the board with the new bit stream. And we feel that although this, probably isn't everything you need to know to go off and do huge Xilinx designs, this does give you a really good starting point to start your next project with. Plus, it gives you a working design that you can build off of and move forward with.
So I've heard one of the most challenging aspects of DSP design on FPGAs is verification. Is there anything special in this kit that helps with that?
There is, and I had mentioned before that in our tutorial we provide these techniques where we kind of show you a couple of tricks you can use to use an RTL simulator to verify that your filters are working, but it's like, come on, these are filters. You really want to see these things in the MATLAB or Simulink environment. So to be able to design, even if you design them in RTL, to be able to then simulate those in the Simulink environment and view the waveforms is really going to give people the sense that it's working.
Yeah.
DSP tends to be not an exact science. It tends to be, you're looking at response plots. It's sort of a good enough kind of thing. So we have a couple capabilities in the tool today. We do have the ability to bring in RTL and simulate it within the Simulink environment. So we call that block box simulation. Xilinx has their own. MathWorks has a product as well called EDA Link. And this would let me use all the power of MATLAB and Simulink to generate my input stimulus. And then it would give me the richness of their visualization environment to do scatter plots or power spectral density plots or whatever kind of plots you needed to see. All that would be available. But the other thing we have is we have what's called Ethernet-based hardware COSIM.
Okay.
Where you can actually place and route the design, program the board, and then the Simulink environment connects to the board through Ethernet. And from that, we're able to pass down the Simulink inputs into the hardware, sort of crunch it on the hardware, and then bring it back up into the environment. And this does a couple things. In a lot of cases, it accelerates long simulations dramatically. Usually somewhere between 20 and 100x faster simulation times for large designs. But then you also have the confidence that your design is running on the actual FPGA and it's still producing the correct results. And you're doing it in a controlled environment where you can stop the simulation, look at intermediate results. You can feed it a specific input waveform sequence, things like that. So it's a real critical part of the design process, and it's fully supported by the capabilities of this kit.
Is there any way we can leverage this verification with our actual analog data?
That is the $10,000 question. Is you can whip up a fancy random number generator or input test sequence in the Simulink environment, but it's really valuable to be able to hook up your own analog input and to be able to validate your algorithm in Simulink using whatever it is that you're out there sensing with the ADCs. And we've added a new capability in the Kintex-7 kit that didn't exist in the previous generation kits, which is a real-time data acquisition mode. We've leveraged the FMC 150 card and some of the system generator hardware COSIM technology to provide a mechanism where we essentially can buffer up a frame of data and then burst transfer it up into the MATLAB Simulink environment, simulate it, and then pass it down and synchronize it. And this has been a feature that it was one of the most common features that our previous DSP customers were asking for. And this does provide just a tremendous value to folks that really need to see if their algorithms are working with their actual data in their, in their specific testing environments. So yes, we have that ability in the tool as well.
Okay. The analog interface card included with the DSP kit seems very capable, but what can we do if we have different analog requirements?
There are a lot of different analog requirements.
Yes.
If you were to go to Texas Instruments, Maxim's, TI's, NXP's websites, they have pages and pages. They have, whole sections of their websites dedicated to medical imaging analog or wireless analog or, all kinds of stuff. It's really a very diverse technology segment. And the card that we ship with the kit is very high performance, but it's certainly not going to be the exact perfect card for everybody. And this is where our FMC strategy is really paying huge dividends in a couple of areas. We have like 25 to 30 FMC cards available from third-party vendors. For DSP, which is the ones that provide the card we ship in the kit, they actually have 15 different cards. The card that we ship with the kit is a dual-channel 250 megasample 14-bit. Curtiss-Wright sells a 3 gigasample per second, 4-channel, for real high-end radar. So we've got this whole ecosystem that's available today that sells FMC cards that will plug right into the kit. You may need to do a little bit of work on the analog interface, but it's been our experience that customers can pretty quickly modify the reference design that we give them for these other kits. Or, in the case of some of these vendors like 4DSP, they actually provide Kintex-7 reference designs for all their FMC cards.
Nice.
And there is one in here that I would like to point out is that NXP is now offering, for people that are looking for serial analog, NXP now has, I believe it's an 8-channel JESD204B FMC card as well. So we've even got a couple different technologies that are available. And when we released the day one that the Kintex-7 DSP kit was available, all 30 of these cards were for sale by the vendors. So, a lot of the hard work we did around the Vertex 6 kit really let us launch the Kintex-7 kit at 100 miles an hour into the market.
Okay, what do I have to do to get started?
Getting started is a simple 3-step process. All of our reference designs are available for download online. You don't need to purchase a kit to download the reference design.
Great.
So if you don't already have Xilinx tools installed, you can go to our website, you can download and register for a free 30-day tool eval, and you can download the reference designs. You'll find those linked at the xilinx.com/DSP website, and you can bring them up in the tools, and you can look at them, and you can simulate them. You can even go through, some of the tutorials that don't require the hardware. But what you really want to do is go out and buy a kit, get everything you need, and start playing around with the Kintex-7 device and seeing what it can do.
Great. Well, thank you so much for joining me today, Tom. It was a pleasure speaking with you.
It was great speaking with you, too.
And before we go, don't forget to click that Download Now button below the player to download a free product brief that further expands on this topic. For Chalk Talk, I'm Amelia Dalton. For more Chalk Talks, check out the on-demand section of eejournal.com.